You probably already know that the area of a trapezium, otherwise known as a trapezoid, can be found by using the formula half a plus b multiplied by the height. But what you may not know is how to prove that this formula works. So I'm going to show you a really simple proof. In fact, it is so simple, you probably wonder why you never spotted this in the first place. There are several variations of the trapezium. I'm going to prove why the formula must find the area of a right-angled trapezium, and then it should be obvious to you why the formula finds the area of the variations, the isosceles, acute, and obtuse trapeziums. Then in the last part of the video, we'll be looking at this mystery shape. I'm going to reveal the mystery shape and then prove why the formula must also work for this. Now let's see why the formula must find the area of the right-angled trapezium. First, let's indicate the height of the trapezium. A simple way to do this proof is by changing the way we think about the shape of this trapezium. I'm going to draw a diagonal line from the top of the sloping edge to the opposite corner. The trapezium is now divided into two triangles. The one on the left has the base of length b, and the one on the right, which is upside down, has the base of length a. Notice that the height of both triangles is h. The area of the trapezium must be the sum of the two areas of these triangles. We know that the area of the triangle is given by the formula half base times height, so the area of the triangle on the right side must be half a times h. The area of the triangle on the left hand side must be half b times h. If we add those two values together, that will be the area of the trapezium. Since both of these values have an h in them, we can factor out the h. And that's going to give us half a plus half b, that's in brackets, multiplied by h. But both values are multiplied by half, so we can factor out the halves as well. And if we do that, the half comes out of the brackets and leaves a and b inside the brackets. And that gives you the formula we said finds the area of a right-angled trapezium. And this simple process works for all the variations. If I swap the right-angled trapezium for the isosceles trapezium and I draw a diagonal from the top of the sloping edge to the opposite corner, we get the same effect. Two triangles, one with a base length of b and the other with a base length of a. So the area of this triangle is half a times height. The area of this triangle is half b times height. And then simplifying, we get the same formula. If I swap the isosceles trapezium for the acute, we draw the diagonal in the same way. We end up with the same scenario, two triangles with base a and b. And so the values for the formula will be the same, and then when we simplify we'll get half a plus b multiplied by the height, and it's exactly the same if we swap it out for the obtuse trapezium. Again, if I draw the diagonal in the same manner, we again end up with two triangles, one with a base of a and the other one with a base of b. The calculations are going to be exactly the same and we'll end up with the same formula. And so that's why the formula works for all of the variations of the trapezium. Well, I know you've been waiting for me to do the mystery reveal, so let's show this shape. What? I hear you say. This isn't a trapezium, it's a parallelogram. This is a bit of a controversial subject, and it depends who you listen to. I think in the majority of cases people will say that this is not a trapezium. But let's have a look at what Wikipedia says about this subject. Wikipedia uses the word trapezoid for the shape and it says, a trapezoid can be defined exclusively or inclusively. Under an exclusive definition, a trapezoid is a quadrilateral having exactly one pair of parallel sides. So under that definition, the parallelogram fails because it does not have exactly one pair of parallel sides. It has more than one. But let's look at the other definition. It says under an inclusive definition, a trapezoid is any quadrilateral with at least one pair of parallel sides. And the parallelogram meets that definition. I've left a link to the Wikipedia page in the description of this video so you can have a look and make up your own minds. The interesting thing is that we can still use the formula to find the area of a parallelogram. Let's swap out the obtuse trapezoid for the parallelogram. And just as before, I'm going to draw a diagonal line from the top of the sloping edge to the opposite angle. And as you can see, we end up with two triangles. So we can just plug the base values in, simplify everything, and we're going to end up with half a plus b multiplied by h. But in a parallelogram, opposite edges are equal. So these two edges are not different. We need to change the top edge to match the bottom edge. And that means that in the equations we worked out, these a's are really b's. So let's just change the last one. So I'm going to change this to a b, and now we get the formula 1 over 2 b plus b times h. But is this the area of a parallelogram? Well, in the brackets you have b plus b, so that really is 2b. And then outside of the brackets you get 1 over 2 multiplied by h. Well, the 2's cancel and you just get left with bh. That is the area of a parallelogram, whether or not it is a trapezium. Well, what do you think? Should a parallelogram be considered a variation of a trapezium? Let me know in the comments. That's it for now. Thanks for watching.
If I swap the right angle for the if I swap the right angle trapezoid, if I swap the right angle if I swap the oh my god, if I swap the right angle trapezium